I don't know. Can you see my full screen?
Not yet, but we can see. Now we can see it.
Yes.
Okay, perfect. Thank you. So, well, first of all, I would like to congratulate all the teams that have successfully finished this high energy TTP2 that I know had been a bit intensive. I would like to really quickly explain how these teams got here. Okay, so the iEnergy second open call was open from October 2022 to the 12th of December 2022. The iEnergy project was looking for a consortium of 2 members to develop new service on top of existing technologies. Okay, the open call closed successfully with 80 applications submitted from 26 countries, and all of these applications resulted to be eligible. Okay. After that, all these applications went through a very exhaustive selection process. We have the 80 submitted that were eligible, and we perform pre-scoring where the 55 applications that had a better approach to the scope of the iEnergy project were selected. After that, 2 independent experts per proposal evaluated the proposals. We created a ranking that was later discussed by the selection committee. And after this consensus meeting of the selection committee, we selected 15 teams to be part of the TTP2 program. This technology transfer program 2 has lasted 9 months. In these times, the teams have been working with the help of the iEnergy mentors, covering 4 milestones: the individual mentoring plan, a prototype mockup, and finally, creating this minimum viable product that has been the last milestone. And now, well, let's see what each team has done, and they will present us the solutions. Thank you very much, and that's it.
Thank you very much, Yolanda.
So maybe Anna will introduce the teams.
Yes. Hi, everybody. So I think that we can start with the presentations, and we will start with AI Flex in Edge. You'll have 7 minutes, and if you have any questions, you can write them in the chat.
Okay, perfect. Thank you. I don't know if you can hear me well because I have some issues with it, so if it's okay. Nice. Do I share my screen, or are you going to put the presentation on yours? I have to share my screen, right? Okay, perfect. Okay, are you watching my screen now?
Yes, we can see it.
Yes.
Okay, perfect. Hello, everybody. My name is Daniela Garcia. I am project manager in Barbara, and Barbara and Cuerva have made this project about deploying AI flexible algorithms in a virtualized substation. Okay, so just very brief explanation of who we are. Barbara, we are product developers, so we act as a solution provider. We have an edge AI platform to manage and deploy AI models in the edge. And Cuerva, it's a family-owned company around the energy sector in the south of Spain, in Granada, and they have different services in the electrical sector, like renewable energy generation, electric energy distribution, commercialization, and some energy services, energy digitalization. So they act as the pilot owners of this project. Okay, just a problem introduction. The increasing number of distributed energy resources throughout the low voltage grid, that it's actually the less digitized part of the grid itself, is producing an increase in the overvoltage and congestion events in the grid. So the purpose of this project was to have a perspective on how the grid will behave in the future and to address some techniques to solve the problem detected. So the main objective of this project was to achieve an accurate forecast.
Yes. Sorry for interrupting, but I'm seeing just the first slide.
Oh.
I don't know if...
Yes, the same for us.
Everyone is seeing just the slide as well?
Yeah. Do you want me to share it for you? Oh, no, now we can see the next one.
Now.
Now we see the
I'm
objective.
going to shut down my camera because I think that my internet is not so good. So maybe I'm going to shut this out and see if I can now, if you can see now the... Are you seeing my screen now?
Yes.
Like the different slides, okay. And if I put it on the presentation mode, let me see. Are you seeing now some other slides than the first one?
Slide number 2.
Okay, I don't know what's happening. Maybe if someone can share the screen for me, I think it's going to be better.
Okay, Barbara have shared my screen. Can you see it now?
Yes.
Okay. You just tell me when you want me to change the slides.
Okay, this one I already presented, although you didn't see it. Okay, then the problem introduction and the next one, please. Okay, so right now, what I was saying that the main objective of the project was to achieve an accurate forecast of user demand patterns from the transformer point of view. So the main challenge we face with this, and the DSOs face with this, is data, because the data from different substation equipments differ not only in the granularity, but also in the time to access the value of the data. So to actually have a continuous streaming of data that can fit the algorithm, a flexible algorithm, was part of this project challenge. Okay, so next slide, please. Okay, so that's why Barbara and Cuerva have joined forces to develop a solution that can virtualize the substation using edge computing technologies and AI algorithm development. So what we do is to have an edge node at the transformation center that it's in the substation Lachar in Granada, and give the real-time access to the data, allowing the development model to be updated without having to wait a day and to be more valuable and accurate. So what we have is to capture data from the different equipment in the substation, and then we have deployed in the edge the AI flexible algorithm. Okay, so if you can... Okay, so basically what we have done is that we have two streaming of data, one from the transformation center equipment and also from the smart meters. So we have a dashboard of real-time monitoring about these two equipment, and then we have the AI model that gives the with the saturation information on the transformation center, and we can give the behavior prediction from the smart meters, we can anticipate to have a flexible solution. So moving forward, I'm not going to just the bit of the architecture. We have used the SAGM model, where we have the field layer from metadata, the user information, some substation data. Then on the edge computing, we have a data management layer with data processing, data storage, and management. And the functional layer, where the demand forecasting and digital twin and the flexible tools have been deployed. And on the market layer, of course, the AI on demand and Barbara's marketplace. Okay, yes, next one, please. Okay, so what is in the edge node, we have some connectors, some data collectors from like Modbus, 104 connectors, SOAP, that collect the data from the different equipment in the substation. Then we have an MQTT and an application that is running on the edge to ingest the data to an influx database. And then the AI model is feeding from the database of the influx database, and it's also having some information about the meteorology API. And all the dashboards, the real-time monitoring and the predictions are printed in a Grafana that I'm going to show you on the next slides. Okay, so this is Barbara panel. That is our panel where we can visualize all the apps that are actually running on the edge node. So you can see here the different applications, as I say, some data collectors like the connector SOAP or the ingester MQTT. Then we can also see the Grafana, and you can also see the algorithm from Cuerva that is deployed in the edge node. Then on the picture, we can also see the data that is on the InfluxDB. You can see here is a query about the information about the transformation center, and we have some tensions and some historical data that has been captured. So moving on. We have also the dashboard about the real-time monitoring. We have like a digital twin about the network, medium voltage network, where we can see the percentage of the saturation of the line, and then we can also see some meters if there are some meters that are having over voltage or are having sub voltage, and some other data about tension, intensity, power. Okay, okay. Then we also have this historical data. Some is stored in the edge, but also this is a cloud platform where it's a Grafana that's in cloud, and you can have all the historical data that can actually also feed the algorithm. And we have the historical data about the saturation, as well meters with over voltage, sub voltage. Okay, moving forward, we have the third dashboard that is the prediction output. So in the first image, we can see the real-time visualization of all the power of all the meters in the substation. Then on the second dashboard, we can see the meteor prediction. We have it contains data about temperature and radiation, and we can see also that it is a 6-hour prediction where 0 is the real-time value, and 1, 2, 3 are the hours the hours predicted. On the third part, we can see the real-time value of the selected meter, where in the filter up in the image, and it's has been as a zero value. And then for the dashboard, we have the actual power prediction of the selected meter, where it contains the 6 predictions, 6 hours before the real time hour. So as I have already said, with the saturation info and the behavior prediction, DCOs like Cuerva can anticipate these flexible solutions. Okay, can I move on? Okay, so just about the market, we have a Barbara Marketplace where we have uploaded Cuerva's algorithm, and it can be added to the library using Barbara's platform. And then, of course, if the next slide. We have also added to the AIoT platform, where you have some videos about what we have done. It's also a database, and then it's a Barbara website, Cuerva's website, and a link also to Barbara's Marketplace to actually deploy this algorithm in an infrastructure like we have created. Yes, of course, this is our contacts. Well, my colleague Fernando Rubio from Cuerva, that it's been also very involved in this project as pilot owners, and of course myself, Ainara Garcia. Here you can have our emails and our LinkedIn profiles. And that's it. Thank you very much, and we'll be happy to answer any of your questions.
Thank you very much for your great work and presentation, Ainara. If you have any questions, as Anna has said, you can write in the chat. Anna, do we have any questions?
No, I do not see any at the moment.
Okay.
In any case, if there's any questions, you can write in the chat and we can try to find some spots at the end. So I think we can move on to the next presentation, and it's AI for CZC.
Hello, everyone. Can you hear me?
Yes.
Yes, yes.
Okay. I'm going to share my screen. Okay. So everyone can see my screen?
Yes.
Okay. So I am Andrés Belalonso. I'm from Inceptive. I'm very happy to present today for cross-zonal capacity, our project when we build a platform for electricity forecasting using machine learning models. Today I'm going to present quickly who we are. Then my colleague from CGS is going to present the problem, the cross-zonal capacity allocation, and then I'm going to give an overview of the AI for cross-zonal capacity platform and the machine learning model that we built during the project. So Inceptive, we are a French SME created in 2017. We are based in Grenoble. We have 2 core activities, a SaaS chatbot platform and our AI consulting activities, which are multi-domain. We help our clients from deciding their data strategy to build models and deploy these models and use on the information systems. And we build our own platform, Igloo, which help us to make the whole process. Our partner is the Electrical Power Transmission System Operator of Montenegro. It controls and operates the electricity grid in Montenegro and substation and switchyards. With their national dispatching center, they are equipped with up-to-date equipment for real-time data acquisition, and they control their network in real time. So, Biljana, you can present quickly.
Yes. Hello, everyone. I hope that you can hear me well.
Yes.
And great. And if you don't mind, I will keep my camera off due to the bad connection I have at the moment. My name is Biljana Ivanovic, and I work in Montenegrin Transmission System Operator as a scheduling in the Department for Short-term Scheduling. And today I will use this opportunity to acquaint you with the subject of this project. The aim of this project is actually the approach was to examine estimation possibilities of AI and to develop a model for the forecast of cross-zonal capacity. The cross-zonal capacity is the amount of transmission capacity. That means the maximum energy that allows to transfer energy between two bidding zones. TSOs have an established procedure for the calculation of and harmonization of cross-zonal capacity on yearly, monthly, and weekly basis. Calculation of cross-zonal capacity is in principle straightforward for those time frames for which scheduled data are available, for example, for day ahead and intraday, which is not the case for time frames for which schedules are not available. That would be, for example, from 2 days ahead up to 1 year ahead. So our aim was to empower TSOs to optimize the allocation and use of cross-zonal capacity in daily auctions by providing accurate prediction of physical electricity flows across the country's interconnection. The model that we use is NTC model. We also defined several statistical parameters and tests which are used to determine the correlation and relevance of data in order to get more precise prediction model. The final model is to obtain balanced net positions needed for the subsequent stages of the common grid models process regarding the time horizon for which there are no market schedules. As I said before, 2 days ahead up to 1 year ahead. So the common grid model alignment algorithm has to distribute the preliminary net positions across all bidding zones until they sum to 0. Here is a consequence of having a better estimation. We would offer more cross-zonal capacities to the market and release congestions, which will further impact on lower congestion prices or no expense at all for market participants. So in the following slides, you will have a chance to hear more about the final results, the results that we obtained in this project. And at this stage, I will pass the floor to my teammates, Andres, so you can take over. Thank you.
Thank you very much, Biljana. So in order to provide a correct estimation of cross-zonal capacity, we need a good estimation of net position. So we targeted 2 days ahead during this project. So we use a high predictive model to estimate the future of net position. We use generation, load, outage, and transmission data. And then, as Biljana explained, they could estimate cross-zonal capacity. In the platform that we build, we start from blue, and then we run.
Arrival flight,
thank you. And then we connect to Ensoe Transparency Platform to retrieve data. So data is retrieved in real time, and the model makes predictions in real time. So in our solution, we have a dashboard that shows the real data and the forecast that we made, and we show many errors. We also made available an interface to download a part of the retrieved dataset and test the model, uploading some synthetical data or some scenarios data. As we computed metrics, we could have an LR matrix that can be integrated in the API of the user of the platform. So the AI model computed the 48 outputs, one for every next hour. We trained it using 2 years, and we tested on one last year. The reason to use less is that topographical the electricity network in Montenegro has changed a lot since 2019 with the connection with Italy. So we were pretty happy with the R2 value with the correlation with the model. but the model make several errors, and the percentage error was very important in a test set. And in the 3 test scenarios that we tested, the model who had a near 80% of error. So the errors of the model were high, but if we use these models, the model forecast, we Bilzona found that we can increase the Montenegro-Kosovo cross-zonal capacity by 100 megawatts. So this leads to a cost reduction starting for 50%, which greatly reduce the cost of TSO to operate the network. Thank you very much.
Thank you. I don't see any questions. Does anyone have any question?
I just want to say that it was a pleasure being your mentor, and you have done an outstanding job, so congratulations.
Thank you, Spiros. It was a pleasure to work with you.
Thank you.
Thank you all. I think we can move on to the next presentation, and it's AI for Helios Plus.
Yes, this is just 1 second. I'm going to share my screen. Could somebody verify that you are seeing my screen and you're hearing me well?
Yes, you can see our screen and hear you.
Okay. Good morning, everyone. We are very, very happy to be here in the E-Energy final event. And we wanted to show you the very big effort that we've done in the last 6 months to create the new Helios Plus platform. First, I wanted to talk about the team that has been involved in this project. First, my company, ConnectThink, which are the AI developers. And here we've had 3 people involved in the project. And on the other hand, we've had 2, the company Iman, which are the data and platform owners and the platform developers. And from this team, we've had 4 people involved. What is the platform Helios? So Helios is a public lightning remote management system. And here in the slide, you can see screenshots of some of the functionalities that the platform has. You can see that the platform allows you to locate the luminaires of the city in a map. It has alerts for when a device is having a breakdown, so it can be repaired, and the intensity of the lights can be regulated to create the maximum level of optimizations. There are a lot of other features in the Helios platform, but these 2 are the most important for the presentation of this project. We've developed mainly 2 services. The first one is the predictive maintenance service, and the second one is gamification and context forecast. The main objectives of developing this project is the integration of the AI services to the platform Helios to create the new Helios Plus platform. And the second one is the economic and ecological impact that this implementation will have. Sorry about that. First, I wanted to talk about the service predictive maintenance, which is an AI product that gathers meteorological historical information, the electrical readings, and the history of the breakdowns of the devices to create an AI predictive model that predicts the breakdowns for the following months of the luminaires of the city. The results of this model have been excellent, with a 90% accuracy score overall and a 50% premature detection of sudden errors, which are the most difficult errors to predict in a lightning system. The second service that we've developed is the gamification and context forecast, which is an AI service that, using the meteorological forecast for the following night, the moon phases and hours of sun, the city events during the night, such as a football match or a concert, and the price of energy, the predicted price of energy, it generates recommendations of light intensity for each one of the zones of the city and for each one of the hours. For example, if we have, for example, if we have a certain night that at 8 p.m. there will be a football match in the center of the city, there will be dense clouds in the sky, and we will have a full moon, the model will recommend to have the lights at 100% intensity. But if in 3 hours the football match is over, everybody goes home, and the clouds in the sky go away, the system will recommend to decrease a little bit the intensity of the luminaire to optimize the cost of energy. Here in this slide, you can see the visual representation of the output of the gamification and context forecast module. The first graph, the green bars, represent the recommended intensity of the lights during the night. You can see that there are some hours where the model recommends to have the luminaire at 100%, and there are other hours where it recommends to decrease around 10% the intensity because of events or meteorological conditions. In the right part of the screen, you can see the aggregation of the percentage of savings by area of each one of the luminaires. So for example, we can see that we have center north, east, we have a football field in the north of the city, different places. We've done some tests with the small city of Spain that it's called Canyelles, and we've concluded that the savings in matters of CO2 can be up to 170 kilograms daily, which extrapolated to 365 days can lead up to 60,000 kilograms of CO2 savings every year. To end my speech, I wanted to show you the final product, which is the new platform, Helios Plus, which is, again, as I said in the beginning of the presentation, a public lighting remote management system, but now it has the two services, the two AI services integrated. In the left part of the screen, you can see the predictive maintenance module working in the AI platform. If you take a closer look into the green box, you will see that here appears the probability of breakdown of the e-box and of the light. And in the right part of the screen, you can see the gamification and context forecast module working on the Helios platform during a certain night. So thank you very much for your attention. I don't know if I have still some minutes left to answer questions, if somebody has a question. And thank you very much for the support. We've really had a lot of fun creating this project and with the communication with e-Energy. Special thanks to our advisors, Yolanda and Sotiris.
Thank you, Jaume. Congrats for your great work here. Thanks so much.
Thank you.
Congrats.
I do not see any questions, so we still have some time. If there are none, maybe we can move on to the next presentation. And this will be AI for Hydro 2.
Yes, good morning, everybody. Let me just share my screen. Okay, so you should be able to see my screen.
Yes.
Let's start the presentation. So thanks again for having me this morning. It's a pleasure to present the results of our project, extending the remaining useful life of hydro turbines. My name is Günther. I'm the co-founder of Lexatexa. And with me in the call is Jörg from our energy partner Salzburg AG, who we co-developed the project with. So we are active in enterprise AI, and enterprise AI basically takes care of all the integration aspects that you need when running data-driven and AI-driven solutions. And we deployed a solution for extending the remaining useful life of hydro turbines. Let me briefly give you an idea about the problem domain. Actually, a very large part of existing hydro capacity is pretty old. That was built way back in the 80s. And so they're like 30, 40 years old. That means we have access to very little data typically. And the infrastructure that we see today is typically not in a state to retrieve real time data. Put in perspective, here's a slide that gives you an idea about when most of these hydropower plants were built and how old they are today. And on the right-hand side, you see some of the conditions of hydropower turbines that we also face today. So the problem really is that a typical hydropower operator today, they more or less fly blindly in terms of what is the status of their turbines, and consider that these turbines, they live in a large housing, and you can't just stop them and walk in and then inspect them. They're closed up, and if they stop the turbine, it's a major activity and a major shutdown time. So what we're doing is what Lexatexa is doing is we provide the software and also, if necessary, the IoT devices to retrofit the hydropower plants, and based on data that we retrieved with our partner in Austria from Salzburg, we've built digital clones of turbines. And then we deployed these digital clones to additional hydropower operators to validate them and to support them in timing their maintenance windows and to get an accurate status of their turbines. Let me go one step back. What you see here is the architecture of our system, of our platform, that basically covers all the necessary steps from integrating the data, covering security, compliance, and covering integration. And in this specific project, we focused on refining and building the AI-driven models and also generating APIs to integrate them. Now, let me run you briefly through two use cases. So we've built digital clones based on two types of data. We've got quantitative data that we retrieved from SCADA systems. And thanks to our partner Salzburg AG, we have access to a very large history of real-world measurements and also real-world analysis of a turbine's status. And then also we work on qualitative data, which basically comes from maintenance reports. The types of turbines that we worked with include 25, 50, and also 330 megawatt turbines. And we got the data and also validated the results in Austria, in the Austrian Alps, where our partner runs more than 30 power plants. And we also validated in Brazil, close to Iguazu, where we worked with a pretty large power plant with four 330 megawatt turbines, in total 1.3 terawatt. So let me give you some data here. What you see here is the system reading in real-time measurements from SCADA systems. And it basically, in the first step, informs the operator about the readings and the status, and also about relevant variables that do have an impact on the specific status variable. One of the two major questions that the turbine operator has to answer is if they continue operating the turbine based on as they did in the past. The first question is, for how long will the operator be be able to run my turbine before I need to go into maintenance? And the second question related to this is, if I, as an operator, want to hit a specific maintenance interval, how would I have to operate my turbine to hit exactly that interval? And what you see here is basically the result of one of our models. You see on the left-hand side the abrasion of the turbine, how it deteriorates over time, and then the operator gets two types of information. In the blue funnel, what you see is the status of the turbine if the operator continues to operate the turbine as they did in the past. And the red funnel, they can actually use the parameters to reconfigure the models and run scenarios, like asking the system, so what would happen if I increase or decrease the number of starts, the operating hours, and other parameters. Basically, as a side product, we use the system to generate anomaly detection plus the explanation of why the system thinks that there is an anomaly. Let me very briefly, given time, show you one example. So the system would flag an anomaly, says, hey, look, I discovered an anomaly. The operator would say, that looks totally normal to me, but then the system would give an explanation and say, yeah, the reading may look normal, but it doesn't make sense given other readings that are also have made at the same time. Now, given time, let me jump a little bit faster forward. You can access our system either as a standalone app with a UI, that's what you see on the left-hand side, or you can access the system as through a REST API that is published on the iEnergy catalog. And we are looking for hydropower operators in Europe to further roll out and to pilot. And at this point, thanks very much to our mentors Yolanda and Spiros. Thanks very much, and looking forward to receiving your questions.
Thank you for your presentation. I don't see any questions in the chat. So maybe we can move on. And the next presenter would be Ergo.
Hello, everybody. I don't know if you can hear me.
Yes, hello.
Okay. So I'm going to share my screen. So we are with Remy Chup, one of my colleagues, and I, Yoann Janvier, presenting you the Ergo project. So we are, we have been working on this project since several months, and so it's a project designed for the energy community and based on AI evaluation. Our team was composed of two French companies. The first one, RTE, you probably may know, it's a French TSO, and the second one is Artelis, so our company, and specialize in applied mathematics and light optimization, data science, AI, and especially in the domain of the energy. So what we have done during this project is to develop a kind of bridge between two existing Python framework. On the one hand, we have Grid2Op for Grid2Operate, which is a Python open source framework designed for AI agent simulation and evaluation and also training. And on the other side, we have Possible, which is a Java framework in order to simulate grids. And so our main goal was to develop a backend, so between these two modules, and to make grid2up evaluation, training, and so on more realistic by using an industrial backend. Backend which is possible. So our project was driven by two main user stories. First one was for simulation, an AI agent, and on the other side we had the train and the evaluation. We have a small video to show you to demonstrate what has been done during this project. Let me know if you can hear sound and so, and if you can see it. Can hear the sound?
No, we cannot hear.
Okay. Okay.
Here we have our 4 assets, and
you can hear it, I guess.
Yes.
Most important one is the GitHub source code. You can find it there by clicking on the link, and we are directly on GitHub with the PyPossible GitHub backend, which is our package. And we can find here on the README all the information to install properly our package and build all the dependencies that are needed for it to work. We have also a precompiled version available on PyPy. Going back on the IOD platform, so we can also find our open datasets, the one that we have created for the purpose of this project. This is named the case 1888 RTs, and we can donate it just by clicking it there. Also, we can find the links to our 2 user stories. The one for using an agent on Grid2up, which is a Jupyter notebook, and the second that will show how to monitor and train an agent with a training script. So here we are on our Jupyter notebook. So first we are going to do some classical imports for Grid2up, the main packages, and from our packages, the one we have developed here. Then we are giving the path to the data, the one that we have just downloaded for our Ergo project. Then there is the description of a function of evaluation that is using a lot of Grid2up function, which is really useful just to have some basic information on how our agent is doing on the grid. Then we are loading our environments, so declaring our backend and the reward class. And then we are initializing our agents. So this is done by creating a dictionary of one action that we're going to do, and then we're going to give that to this agent when changing nothing. So we're going to do the change described in the dictionary, and then nothing for the rest of the chronics. And then we are launching the evaluation of our agents on the 4 chronics. For the results of this first user story, we can see the evolution of our agent on each step of each chronics. So for the first chronics, we can see that our agent is dying at 49 steps. And for other chronics, we can see that this is at the 15th one. And this would be the same result for the others. This is completely normal because how our chronics are made. And we have a little summary of all the chronics and the associated score, and also the time steps where the model just died. So we are now looking at our second user case, which is a script for training an ML agent and evaluating it. We are doing it on EA14 data set because it will be faster. First, we have a function that is able to split dataset into train and evaluation dataset regarding the chronics, and then we are using these two datasets to train our agents. Here, our agent is a PPO RL agent, and this will be trained for 10,000 iterations. Then we are evaluating our agent on our validation and our training dataset, and we can see the results printed at the end. So after running the script, we can see the results that are just there. And you can see, for example, that for the two chronics selected for the training, our agent is doing pretty good, but for the validation test, that our agent is doing pretty badly. But of course, we haven't made any optimization for it. Thanks for watching.
So thank you for watching. Just a few words about the Ergo project. So we had some KPIs to reach, and so either towards the code or even toward environmental and business cases, and which have all been reached. So thank you for your attention. Thank you for all our team. From Airtel Artelis, and thank you to our mentor, Leonardo Callejas, also.
Thank you. Thank you for presentation. I do not see any questions in the chat. I don't know if anyone has any question. Okay, if not, we can go to the next presentation, and will be Aria.
Hello, let me share my screen, just 1 second. Okay. Okay, here we are. My name is Federica Guerrini, and I'm from Amigo, and today I present to you Aria, which is our cutting-edge service dedicated to transforming wind forecasting for the renewable energy sector. In a world where renewable energy is not just a choice, but a necessity, accurately predicting wind speed becomes crucial for maximizing efficiency and reliability. Predicting wind speed is a huge challenge. In the context of energy trading, wind power fluctuations can be a double-edged sword. Wind power forecasting is here crucial for making effective market strategies. As wind energy is variable, it can easily cause grid imbalances, which are costly for energy traders and also for wind farm operators. Accurate predictions here are essential for mitigating balancing costs. These problems arise because existing meteorological forecasts are imprecise at the spatial scale of wind farms. We can use artificial intelligence to refine these weather forecasts and account for local wind patterns and reducing uncertainty at the level of wind farms. For this reason, we have developed Aria, our tool for enhanced short-term wind forecasts. Amigo made a partnership with ANEV, which is the Italian Wind Energy Association, which provided us with crucial expertise on the wind energy value chain as well as with data. In fact, data is foundational to Aria. We use real data from wind farms, but also existing meteorological forecasts to be, in fact, improved. Also using other types of data like climate data and also land monitoring data. All this data is given as input to novel AI models that are dedicated to these tasks to finally provide higher solution forecasts of wind speed and of the related energy generation. This is an overview of the architecture of Aria, which has, of course, an ingestion module to manage all the data I previously listed. This data is, of course, pre-processed. And then there's the core of Aria, which is the AI models that are dedicated to perform the tasks of wind speed forecasting and also of the related energy forecasting. Our technology is based on an LSTM architecture with an encoder model and a decoder model, which understand the historical time series as well as have an insight of the future using the forecasts. All this data is used to be given to our API service, which provides data to the users. So which is unique about ARIA? ARIA is able to provide users with wind and power predictions, which are up to 50% better than those that would be obtainable using regular meteorological forecasts. And this is possible also because ARIA is customized for each wind farm. And this ensures that the forecasts are tailored to that wind farms and really useful for making decisions. And finally, ARIA forecasts are delivered through an API that ensures security, timeliness, and easily integration of the data into existing processes. The market opportunity for ARIA is very interesting and rather unexplored, especially in the wind energy sector. The TAM for climate services in the energy sector is about 3.3 billion worldwide. And we currently aim to work in the Italian market and then scale up to the European market, where the SAM for this kind of climate services is about 600 millions. ARIA, in fact, can aim at obtaining a 60 million market, starting from the Italian users and then growing up. And we aim at targeting as main users, energy traders, and as secondary customers, the wind farm maintenance managers. The ARIA business model is B2B, where the ARIA API is provided to users through two scalable solutions, subscription and pay-as-you-go. By 2025, we aim at reaching more than 200 users over Italy and Europe. We want to provide our service at an average of 800 euro per megawatt installed in the wind farms of interest. And this will allow us to gain up to 6 million by 2025. A huge project of this kind is not just about technology, it's all about the people who actually work on it. Allow me to introduce our exceptional team, which is a group of dedicated experts in climate, data science, and renewable energy, who are the driving force behind ARIA. As we stand at the forefront of renewable energy innovation, ARIA is not just forecasting the wind, but it's helping to build a more sustainable future. Thank you to iNergy for making this journey possible.
Thank you. Thank you so much.
Thank you.
I don't see any questions in the chat. Does anybody has any question? Okay, if not, we can proceed to the next presentation, and this will be CNROPT. Sorry.
Hello from Greece. I will start sharing our presentation. Can you please verify that you see the presentation?
Yes, we can hear you and see the presentation.
Okay, hi. We are very excited to present CNROPT. CNROPT is the project that we did for iEnergy. Is called CNROPT based on charging network rollout optimization. So the aim of this project is to optimize the charging infrastructure rollout. This project was carried out by SLOA Limited, which has offices in Cyprus and Greece. So the Greek office was doing the work here in collaboration with the University of Zagreb from Croatia. So with the collaboration with the University of Zagreb, we were able to get a lot of information about the charging sessions in the whole country and develop a tool, MVP tool based on artificial intelligence for charging network rollout planning. So for the challenge is that we're going to have in Europe many million of new public charging stations and the operators, they have to make sure that they are going to do the best decisions, make the best decisions on deploying and investing in these charging stations. There are studies, European studies, where we can increase the occupancy in a significant way if we do optimal selection and distribution of the locations where the charging stations are going to be placed. The problem is that currently the stakeholders, they don't have very sophisticated planning tools for planning the infrastructure, basically where they are going to put the new sites and how much capacity they actually need to invest there. You understand that putting more capacity than needed is a wasted investment, but there is a big danger that if we don't put the necessary capacity, we are going to have a problem with the customer experience, and there's going to be long waiting lines for customers to charge their cars. So what we did is the solution that we proposed and we have implemented in Synerop is we have used basically first of all the data from the raw data coming from the charging stations. So we processed all the sessions for each individual charging that has been done for the last 4 years in Croatia. So we had a very big data set that thanks to the University of Zagreb. And we combined this information with a lot of other reference information. For instance, OpenStreetMaps, here maps for the street network, demographics, showing the population density, etc. We also took into account all the EU directives for the planning of charging station networks. For instance, there is a directive saying that in a particular highway network, every 60 kilometers there should be a charging station. So basically all of this information is processed and we use geoanalytics and deep learning AI models to provide plans, and we provide them through an interactive visual tool for the charging station network operators. So we have tested a set of laboratory AI algorithms, ARIMA models, transformer models, LSTM models, etc. We created a very, let's say, sophisticated that layered geographical data set in a state-of-the-art GIS infrastructure. And the technologies that we have used in order to do all this is on the right hand, we have the training infrastructure and the training architecture. We use state-of-the-art PyTorch and NVIDIA hardware in order to train our models. These models have been really very demanding in terms of computing power. On the left-hand side, we see how we can exploit this information. So we developed a very sophisticated geographical tool. On the back end, we use the database, the PostGIS for the reference layers, and Flask for the Python Flask for the API layer. On the front end, we use state-of-the-art JavaScript with a Nuxt JS framework and leaflet maps, among other things. So one glimpse of the tool is like this, so we can see and manage the whole network. The data that we have been using look like this. So this is just an example of a particular charging station, and we pre-processed the charging sessions into time series. So this is the historical evolution. We see the trend, but we also see the seasonality. in the summertime, let's say, for instance, holidays, when people move more. We have also identified the daily, let's say, pattern of charging, which is very important in order to plan the demand and because there is a very high peak of demand at certain hours. So now the tool is looks like this. So for instance, here we have pick a particular charging station. This is a charging station in a rural area. We can also see on the left-hand side, we can see the actual information about the utilization on the charging stations, but we also see the coverage. We developed the coverage that has to do with a dynamic polygon we create based on the street network and the range that we select that some driver is willing to drive to go for charging. For instance, here we see the 40-kilometer range of a particular charging station. So moving on, for instance, here we can see the combined effect of all the charging stations. The different colors that we have in the markets, there is an indication about the utilization. So the warmer colors mean higher utilization. For instance, now we are seeing an example in downtown Zagreb, where we have a high utilized station. And also here we can see on the left hand, in blue is the historical values, and the red it's the forecasted values with the LSTM model. So we can have very high accuracy in estimation of the next days and months. And this is crucial in order to plan how the network has to evolve. We have in mind that a new charging station takes, let's say, around 6 months to be built after a company makes the decision. So the next step is in the tool, we have a possibility to add a new set of candidate locations. Here you see them loaded on the map with a plus sign. So the plus sign means that there are new sites that do not exist yet, but we want to score and see how well they will work in the future and how much traffic they can absorb. So for instance, here we can see that this new data set, for instance, one candidate here in the Dalmatian coast is going to receive pretty high utilization, and it's let's say a lucrative place to select among the others. Another example is another location in the coast, but which may not have a very high utilization anticipated, but we can combine this with information about the potential coverage that it will provide. So it's more, let's say, a holistic approach to the tool in order to select the best candidates that provide both coverage and capacity. So this is how the interactive tool works. Some examples of the results, we managed to get from LSTM models much higher accuracy than the baseline ARIMA models, which are used, let's say, they're very common machine learning models to use for forecasting. Then a few numbers we can share that we used 350 locations and around almost 400,000 charging sessions. So having said that, we can share with you some results. For instance, this is how much we anticipate that we can improve the performance of the network in terms of customer experience. So in the left hand, we have the current quality of service. In the middle, we have the forecasted unoptimized, and the right we have the forecasted. So we can reduce 20%, let's say, the waiting time. We can reduce much more the sessions where we anticipate to have let's say, high waiting time. And moreover, in order to understand exactly what is the effect for the customer experience, we developed a KPI called the Net Promoter Score. Here we subtract, let's say, the happy subscribers minus the unhappy subscribers. And the big take from this chart is that from 67%, we managed to increase it to 76%. These customers, the 9% that we managed to achieve, is representing customers that are going to be promoters of EV usage, electric vehicle usage, and will help the adoption of this technology with a very important effect to carbon emissions. So here we can show you also some challenges that we had with the data. There are a lot of things that can, let's say, happen. For instance, there are changing metering say regimes. The touristic sessions also create a big change in the behavior. And of course, we have missing data. So all of these parts have to be worked before we could run our predictions. The results, as suggested by the consortium, is that we have created in the AI on demand catalog the entry for our tool and our solution, and also the model is presented also is implemented also in the AI for experiments, so it's ready to be used by potential parties that need, let's say, to perform this work. Of course, we will be more than happy to show this MVP to charging station network operators. We have already a pilot with Hrvatski Telekom, which is an operator of charging stations in Croatia and parts of other parts of Europe. So we hope that this is next year is going to be a commercial product. This is, let's say, some examples that we can provide more information from the tool. For instance, we can produce the geographical, the population coverage of stations, where we can see exactly where and how we can achieve the coverage of the whole population of a country using open source data. Having said that, this is my contact information. We will be more than happy to answer any of your questions, and I would like also here to thank our mentor and our partners from Zagreb for the great work that they have done helping us. Thank you.
Thank you for the presentation. I see that we have a question. Maybe you can answer quickly since you are a bit out of time. Do you have reliable sources for population density data? It is also interesting for demand load forecasting.
Yes, yes, these data are available for let's say for whole Europe. As we saw here, there is a good granularity of this information, and it's very useful. For instance, let's say we have a raster, a population raster that we created by downloading data from European sources. I think we used here map, but I have to verify that, so I can share the source. Let's say if you can send me an email, I can give you the let's say exactly the source. So there is a free, yes, there are accurate free sources of population rasters.
Thank you. I don't see any other questions, so I think that we can move on to the last presentation before the break time. So I'll give the stage to Emergent.
Hi, this is Spiros for the Emergent project. So let me share my screen and let me know if you see it. Can you see it or not yet?
Yes, we can see it. Thank
Full
you.
screen?
Yes.
Perfect. So I'm Spiros from Plegma Labs, and today I will present you our project together with Manifest Services Facility Management. The project title is Emergent, a user-driven energy management system for energy efficiency in facilities. Before beginning, I would like to thank the iEnergy Consortium for the opportunity that is given to us to work on this project, and also our mentor, Christos, for the excellent collaboration. Some quick facts about the two companies of the consortium. Plegma Labs is an SME that does business in the areas of IoT in general, especially on IoT for energy, smart buildings, smart homes, advanced analytics, and industrial IoT. And also, Manifest is one of the most reliable facility management providers in Greece, and Manifest has won multiple awards and also has big clients like Siemens, Mercedes, etc. regarding facility management. The challenge that we try to solve with Emergent, as many of you know, around 75% of the buildings in the EU are energy inefficient, and there are some energy management system solutions that try to do things like demand forecasting and energy efficiency recommendations, but in most cases, the demand forecasting tools available for the buildings mostly use a separate AI model like a neural network for each building, which leads to overfitting, is not scalable in case that we have thousands of buildings in our database, and also we can face cold start problem issues where limited data are available for specific buildings. For example, when a new building gets onboarded in the platform and has just few data available. Also, existing energy management solutions, when they adopt energy efficiency recommendations, they do not take into account into their mechanisms the most important asset, which is the users themselves and their feedback. So what we do basically in the Emergent solution, first of all, we do multi-level energy demand forecasting, both for buildings and their assets, and we do that in a generalized way that we'll discuss in the next slides, so that we can provide forecasts for any kind of building if and if they have limited data. And we also use this forecast to do energy efficiency recommendations that are user-driven, since they take into account also the feedback of the users themselves using reinforcement learning. And our system is fully modular and can be used from single buildings and facilities that are much bigger, like campuses or districts. A few more words about the pipeline. So we can see that on the left we have facility data coming from Manifest services in the case of the iEnergy demonstration, and the energy data from the buildings and facilities are collected in the EMS platform, which uses reinforcement learning to make energy efficiency action recommendations to the end users through some kind of interface. In the next slides, we will see the exact format of those recommendation actions, but you can imagine them like recommendations to turn on or off specific devices or assets. And then the users can also provide their feedback on those recommendations, and the EMS systems use the feedback to continuously train itself using reinforcement learning, and also takes into account consumer level and energy demand forecasting. So a high-level presentation of the energy demand forecasting pipeline we utilize. Basically, as you can see on the left, we use energy consumption data for individual consumers or facilities, which are utilized to construct energy profiles for each building. Imagine that as a set of statistics that represent each building with the available data we have. And these energy profiles are also used to do clustering. And we say it double clustering because we separately do clustering for time series data and for more static data with no time series characteristics. And then we just use the last 24 hours or the last week of consumption data to predict the next hours using a deep learning model with an RNN architecture that predicts the next hours with high granularity, for example, hourly granularity. And the fact that when making predictions, we only use the past week of data at most, and we use we train a single model on hundreds of buildings, for example, on public data sets, and maybe we can then fine-tune the model on the target facilities using transfer learning. This gives the model the ability to make predictions for new buildings and facilities with very few data available. And regarding the energy efficiency recommendation component, without diving into too many details, as you can see on the left, the reinforcement learning pipeline of the model is that it makes recommendations for specific assets on a facility, like turning a specific asset on off. And the state at its time slot can include many things, like the status of the devices, the energy prices, and the forecasts for the energy demand, etc. And the overall goal, which is incorporated into the reward function, is to minimize the energy costs. And in order to do that, the model takes into account the aforementioned forecasts, historical time series data, and the user's feedback. And as you can see on the figure on the right, which has a specific 24 hours for a given facility, and you can see with red the energy price throughout the day, and with blue you can see the device load, and the agent makes predictions for the device load, sorry, recommendations, not predictions, for the device load at hours, let's say, outside of peak energy prices. So it meets the goal of minimizing the cost for the facility manager. This is some screen from the emergent MVP. This is the demand forecasting screen. On the top, you can see the forecast for a specific facility for the next 24 hours. And on the bottom chart, you can see the historical analysis of the actual energy measured from the meters compared to the forecasted one. And regarding the recommendation screen, where the user can see the energy efficiency recommendations, you can see that for specific assets, for example, washing machines or air conditions or ventilation systems in this hotel facility, the agent makes recommendations to turn on or off specific devices, and the users on the right can provide their feedback in the form of accepted or rejected. And regarding the AIOD contribution, we deployed following the instructions, the energy demand forecasting module and the energy efficiency recommendations module as AI prediction models, and we also provided an open source data set to the AIOD platform as a energy data for buildings. This data set came from Portugal, from Elergon, regarding, if I remember correctly, 370 buildings. And to conclude, some KPIs for our project, we managed to make the demonstration for 6 facility buildings, with 15 assets in total, like washing machines, boilers, air conditions, ventilation systems, etc. our users were 6, since its facility had one building manager, so our target users are building managers. And we collected at least 78 responses for feedback regarding specific recommendations. As I showed you, we incorporated the 2 services in the AIOD platform, and the forecasting error for the demand forecasting component in terms of weighted mean absolute percentage error was 13%, and the total uptime of the services was above 99%. So thank you for today, and happy to answer any questions.
Thank you. I don't see any questions at the moment. So maybe we can have a 10-minute break, and I'll see you all at 12:35. Thank you. Hello, everybody. Welcome back to the second part of the event. I think we can proceed to the next presentation with eModel OPS.
Yes, great. Thank you so much. So I will share my screen. So I believe you can see it now. So yes, we are the eModelOps project. So this is a collaboration between Rebase Energy, which is a digital energy startup based in Stockholm, Sweden, and Modity, which is an energy trading company based in Lund in Sweden. And yeah, I'm Sebastian. I'm one of the co-founders of Rebase and will present this project for you. So this is the key or the core team that's been working on this project together. So it's been Emily, which is working with power trading at Modity side. We have Henrik, full stack developer, and then me that's been taking a project management role. So the challenge in the energy system with more and more weather dependent and intermittent renewables is really about the balancing. So that's what we're focusing on at Rebase. So we have all these different types of forecasts that you want to create in the new sustainable, renewable, weather-dependent energy systems. And you have all these different types of applications that you can see here in the middle column. And of course, this is all to reduce cost, reduce risks, and increase profits of the operations of the whole system. And what we've been focusing on in this project has been the wind power side and the trading application. And specifically, we've been focusing on ice loss forecasting, which we have seen to be a big challenge when it comes to handling balances in the energy market. So ice losses can be quite difficult to predict, and that's what I will talk about today. So first of all, so Rebase, we're developing a platform where we make it easy to kind of deploy these models, to customize the models, to make APIs, to streamline data flows into downstream applications for decision making. So that's kind of where we come from. And in this project, we've been working specifically on three different sub-goals. One has been developing the eModelOps platform, working around ModelOps and MLOps. Here we've been working with state-of-the-art technologies like Dagster and Great Expectations, and also developing our own toolkit. We've been working on a specific vertical industry challenge. So integrating data APIs, developing models to predict a specific application, which in this case is the ice loss application. And then thirdly, we've been working on developing open source models. And these open source models we have deployed to the AI on demand platform and also demonstrated their capabilities in terms of the KPIs that we set up the project. So this is kind of like the vision slide of the project. So what we created through a workshop together with Modity in the beginning of the project. So it's all about connecting with the current data sources that are available at the Modity side. So these data sources have been other APM systems from wind farms and solar farms, including Greenbyte and Basefield, integrating with third-party forecast providers, and then provide a dashboard, an API, Python-friendly API that enables to extract data into downstream decision-making processes. So the technical view of the platform that we're building and the different technologies that we are working to integrate, you can see on this slide. But I think that the main difference from the previous iEnergy project that we've been working on here in the second project is really the switch over to Dagster as the main orchestrator and pipelining framework. And we switched over from Airflow, and this has enabled us to iterate quicker since there is a clear separation between the runtime of the Docker containers and the runtime of the actual orchestrated pipelines. So a little bit on the timeline. So we started the project, we developed the proof of concept on the mockup. We had as goal as integrating the data sources, developed two different algorithms, one on blending energy forecast, another one on an adaptive online regression algorithm. And then 2 months of actual testing. And we've done now 1 month of online testing. And I hope that I will have time to show that as well in this presentation. So just as an example, what is it that we're trying to do? So here's an example of a verified icing event that happened on the night between the 4th and the 5th of November. And the icing event is taking place around here. So this is the prediction in blue of the icing event. And the orange line shows the estimate of that icing event. Of course, there's no real signal. So all the estimates are only use that estimates. And as we see here, we didn't predict the icing event, but as we roll forward, we still don't predict it here with this model that was created at this time here. But as we roll forward time, we see that our model is becoming more and more confident that this is actually indeed an icing event. So in the end, this provided information more than 1 day in advance, 24 hours in advance, to be able to use that data and to basically improve the energy trading and the balances better. Here's the same view, but as a continuous time series. And what we're looking at now is the green line being the actuals and the blue line being the 24 hours ahead forecast. And here you have the more aligned forecast that is continuously updating. So I wanted to have very just short time to also show a demo of the platform. So let me share the right tab for that. So this is how it looks like right now. So we have the ability to go back in time to look at historical data sets. So this is what I just showed in the graph. So you have the actuals versus the predictions. And right now we're actually looking at going ahead an icing event that is happening as we speak right now. So the question is when this ice loss event will reduce. So we have icing on the wind turbine blades that is built up, and the question is, of course, when will this be reduced? And our model is predicting that this will happen during the night today. And if we're looking a little bit deeper into why the model is predicting that, we can look into this view. And we can see here that the wind speeds from the different weather models is picking up. And that we have understood from Oddity and the expert meteorologists working in the trading floor, that is a clear sign that, an indication that ice might loosen up because of the high wind speeds, so that it will fall off the blade essentially. In addition to this, we developed 3 different assets that we provided to the AI on-demand platform. So one was this short autoregressive open source model. The second one was the blending model. And the third one was a data validation based on Great Expectations open source framework for data validations. So future work from here is to deploy these models on more wind farms to get more data and more confident in our predictions. Second is to improve the data visualizations. Over the course of this project, we got several feedback from the industry partner Modity. So we have several ideas on how to take this forward to the next step and make this visualization more intuitive and useful. We also are looking into how you can improve the persistence of icing. So there's essentially 2 different physical processes involved in the icing of wind turbine blades. One is building up of ice on the blades, and the second is persistence of ice. And we want to take the next step and model those separately and not all at once as done in this project. And lastly is about explainability and interpretability of the models in order to improve further the usage of the models. So that's it. Here you have the contact details for both us at Rebase and Modity, and happy to take any questions. Also, big thanks to our mentors, Yolanda, Thomas, and Sotiris for all the great collaboration and support during the project.
Thanks to you.
Thank you. I don't see any questions in the chat. There was a small change in the agenda due to time constraints, so now we'll have Spire as the next presenter.
Thank you so much. Sorry for this change, but I had to leave at 1 CET. Give me a second to share my screen. Can you see my screen?
Yes.
Okay, I think it's not in presenter mode, right?
Yes, we can see it full screen.
Okay, cool. All right. Hi, everybody. I'm Mike Ramsadakis from Plexus, and together with Elvan, we have participated in the Spire project. I'd like to thank the iEnergy Consortium for this opportunity to have this project. Spire is all about holistic predictive maintenance of solar panels, and this is a small presentation for the final event. The challenges behind what we do is that the solar panels energy production has been and is significantly reduced. And this is mainly due to reasons such as soil or dirt deposits or cracks that can happen. This could lead to 17 to 25% reduction, according to some surveys. The cracks can allow moisture, dust, and dirt to enter into the cell. And this could affect the anti-reflective coating. The bus bars of the solar panels could cause overheating, which in turn could cause damage to the inverters and batteries, which are the most expensive parts of solar installations. So what we want to do, we want to build an edge AI platform that has a twofold approach. One is to present and give to AI service providers the opportunity to develop, train, and deploy models at the edge. And on the other hand, to adopt by solar farm operators solar energy AI applications, which could ensure full control of their data. Thus solving the issue and the challenge of data security and privacy, which is very important also for energy communities. Spire comes as an add-on to cleaning robotic solutions, and that means basically that solar farm operators can streamline their maintenance schedules, and also we can offer rapid deployment of data-driven AI-powered predictive maintenance algorithms. You can see here the robot of Elvan, called SAV3, in an exhibition, and some available data that we had, and we built on them and created more with the demonstrations and the testing side. The final solution architecture can be shown here. You can see three main components: the cloud space, the edge nodes, and the embedded systems, so the robot. And the Spire client has been released in the AI on Demand platform. The demonstration site that we had, the demos, is in Paeania, so it's in Attiki, Greece. Both of the companies are in Greece, so we went to Paeania to test this. You can see the demonstration site plus the camera in, let's say, on top of the robot that was running and provided cleaning. The user interfaces, here is the AI developer's user interface, how it looks like. I will play this a bit quickly because I don't know if I have much time. So you can see here we have the signing in screen, the home where you can see or your notebooks, etc. We utilize a Kubeflow for this solution. Very basic. The notebooks, you can click on them, you can connect on them. You can also run, as I said, ML models on the edge, and also instead on not only inference services, but also training. Let me go quickly through it. Here we have also utilized Elira, another open source project which you can combine different pipelines, different notebooks into a pipeline, sorry, and you can edit attributes such as the CPU, the RAM, and other things that you want to utilize in the relevant node. For example, here are some properties that you can see. We can also select to which a node this specific pipeline or notebook can run. And you can see here an endpoint. We have created one. It's an inference service for tracking, let's say, the dust and the cracks, the pipelines, etc., etc. Going quickly through them. Okay, here you can see arguments, the YAML files, etc. Some experiments, some runs, some artifacts created. All right, moving to the next slide. And here is the solution provider's user interface. You can see quickly how it looks like. So first we had the map, the field view, and then by selecting one robot, you can see how the robot started, say, the cleaning, and then you can see the prediction that we do below the camera speed. Here we tested this with brown, let's say, sand, which mimics a lot the dust. Going quickly through it. And here we also tested it with white sand. Okay. All right. Let me move to the next one. We also tested loose bolts detection. So the camera had an IMU on top of it, and we could check how this IMU it gave us information such as loose bolts or pumps. And we tested it with a broken PV panel, and we had great results. Here is the confusion matrix of both training and testing. So we had approximately 99% of accuracy on this. Here are the KPIs that we included in the project, and we are pretty much there. Some of them are a bit below, like the detection of the dirt and the defects, but there were issues regarding the scenario that we run, and we had slightly less percentage. But hopefully in the next iteration and with a few improvements, we can succeed on the number. The market and the business model. So as you understand, we're talking of a very big market that this could be launched. And the way we want to operate this is that Plexus will provide, as I said, Spire as an add-on, both to solar farm operators or to inspection service providers. And here is a small business canvas that we have created. The expected, let's say, core revenue stream will be a physical node that will be added as an add-on, and this will be approximately 500 euros per year. And we expect to launch it. We are right now in contact with two solar farm operators, one in Greece and one in Dubai. Thank you so much, and I'm happy to take any questions.
Thank you so much. I don't see any question, so I think we can move on to the next presentation. That would be FlexiGrid.
Hello, everyone. Do you see my screen?
Yes.
Okay. So I'm Keros Salib, and I'm software engineer at TechBricks, deep tech venture studio based in Rome, Italy. Together with our talented team at TechBricks, we have designed a technology solution to help the transition of a sustainable energy system. We have designed FlexiGrid. While in the past, the energy system were centralized, and today the grids are highly integrated, and in the future, these are becoming even more intelligent, decentralized, and self-balancing. Self-balancing means that the grid will be able to predict the production and the consumption, which involves prosumers, smart industries, energy communities, and electric mobility, to adapt the dynamic curves between renewable production and real-time consumption. Our vision consists in two challenges. On the business side, we aim to enable the real-time smart energy demand and flexibility of distributed energy resources and prosumers in smart grids. On the technical side, we aim to provide the leading solution for energy management by performance and AI and IoT technology backed by distributed ledger technology. Our solution focuses on smart demand for energy-intensive industries and households. IoT that monitors the consumption and production in real time and collecting data from existing IoT devices or smart meters. Artificial intelligence module that elaborates and predicts the consumption and production curves, which has been actually developed during the energy project. Then finally, suggest to the prosumer the smart actions. Lastly, all the transactions are stored on a quarterly hour on our DLT. So imagine a future where smart homes with domestic storage interact with distributed flexible energy resources to the smart response and switch from production to consumption to rebalance the grid. This can potentially reduce their energy bills to zero with an aid of intelligent energy management system. Within the last months, we have developed AI models to predict energy consumption and production, and we have created the dashboard for our clients. Today, we are able to introduce load, production, pricing, and cost analysis, and introduce optimization for energy-intensive industries by forecasting the optimal load profile for bidding and energy market. Here we can see an example of our dashboards. So on the left side, we have the energy production. We can see the chart for the realized and versus the forecasted one. And on the right side, the consumption one. On this slide, we can see a layer architecture. This was already developed before the energy project, but during the project, we have enhanced our data ingestion layer. We have integrated multiple data provider and solar systems. We have developed all the AI layers, so from data processing, the machine layer, and all the deployment. And we have integrated all this by API layer in our platform. This is a deployment architecture. So we have deployed a new data lake, which performs better with a large amount of data. And we have developed the services that contains our AI models during our Kubernetes cluster. This is a KPIs we have declared. Actually, we have achieved all of them, and some of these KPIs, like the managed capacity, we have exceeded our expectations. So by forecasting the production, energy, and the consumption, finally we can achieve our goal to optimize the energy transactions between assets. This is our team. A unique combination of technical and business skills, including MBAs, 4 PhD, and more than 75 years of experience in the top multinational companies, financial and energy included. They are some of our partners that helped us during the project for data collection and AI development. Thank you for your attention, and special thanks go to the iEnergy team and our mentors from engineering. I don't know if you have any question or...
Thank you so much for your presentation. I don't see any questions. So maybe we can proceed to the next presentation. That would be Jem Green.
Thank you.
Hi, everyone. It was really interesting to listen to your presentation. I hope you see me, and now I will start to share my screen too. Do you see the presentation?
Yes.
Okay, hi everyone, I'm Matteo from Energinews. Today I would like to present you our project that was called Gem Green. So first of all, let me talk a bit about just 2 slides about the partners. First of all, Energinews, so my company. We are now part of MAPS Group, that is like a company in Italy with 12 offices and more than 300 employees right now. We were acquired during 2022, in the last quarter of 2022. And so now we are part of one of the 3 business units of the company. What we do mainly as Energinews, we continue to do energy efficiency. So we were like a company focusing on monitoring and analysis of energy, obviously, for industrial customers and tertiary customers. And MAPS had very strong competencies in renewable energies and in what we call renewable energy communities. So in Italy is CER, but in EU is REX. So now altogether, what we do is we created this business unit, energy business unit, and we focus on energy efficiency and energy flexibility. We have like quite a big ecosystem of partners and also clients in Italy, mainly in Italy. And we proposed this project in collaboration with one of our top customers, that is the Calzedonia Group. More or less, I think you know who is Calzedonia, but it's like one of the leaders in the clothing sector, in underwear sector mainly, with more than 5,000 stores in all around the world. They have altogether 8 brands and more than 40,000 employees. Most of them are women, and with half of them under 30. So it's like a very interesting company for us, because they want to innovate, they want to be very sustainable in terms of energy consumption. So it's like a really interesting partner for us to collaborate with. So what about the project? We have like a platform that is called ROSE, and this platform is, as I said before, is quite big. We do a lot of stuff, mainly based on artificial intelligence, but yes, we have a lot of modules, completely cloud-based with edge nodes. So I heard a lot of similar architectures in the previous presentation. So I mean, we are more or less on the same page. During this project, we focus on a specific vertical, that is retail, obviously regarding Calzedonia, and is like including employee engagement into a platform like our platform, like an energy analysis platform. So the idea here is like that the energy analysis and the energy efficiency is not something meant only for energy managers, but it's something that also the employees can contribute to. And so our ambition is that this, like adding also the employees into the loop will positively influence also the energy efficiency of the buildings. And so how we measure the success of this project mainly on 4 KPIs: user interaction and user engagement, and then reduction in energy consumption and improvement in well-being. That's quite relevant. So the first 2 are how people are now interacting with the application. We are just a small group of people, obviously, because it was a pilot. We expected a couple of numbers, and we were able to achieve both of them. And also we expected like some more objective KPIs related to energy consumption and also improvement in well-being. Regarding energy consumption, we were able to achieve a 7% of energy saving overall in the pilots that comprises 20 shops and 3 industrial buildings. So we were able to achieve this energy saving in the last 6 months compared to the previous months. and also an improvement in well-being, because part of the project is also optimizing the HVAC systems within the shops. I will show you later on. Yes, the main ambitions, as I said before, is like to empower employees to be part of the decision and changing process. So during the project, we created or extended 3 different algorithms based on the artificial intelligence. The first one is like a comfort optimization engine. So it's a solution that at the end configure an HVAC system. So it's a system that provides cooling and heating, mainly based on air, for small shops. It's something that we have usually in offices and shops and so on. And so what we do is like to forecast some parameters. So in terms of the comfort, in terms of energy consumption, in terms of different parameters that will provide the possible future situation. And then we choose the best optimal strategy in the next 6 hours to provide the optimal comfort, because these are tertiary building, and the main focus is the comfort, it's not the energy saving. But while providing the most comfort, we also try to minimize the energy consumption. And the idea is like this system is always learning and is always training. Okay, so we use convolutional neural network and to do the forecasting and optimization engine. And then we created that anomaly detection engine, so that the basis of the gamification, so the involvement of people, the employees in the loop, is to be able to detect automatically anomalies. And these anomalies for us are situations where we have wastes, situation where equipments are not working properly, or situation when we have a wrong behavior by people. Okay, so all these situations for us are anomalies. And then so the third step is the gamification. So if you look at the 3 algorithms, the first one is something that works without people. Okay, and the other 2 is how we involve people in the loop, finding the anomalies, and also through a gamification engines actively involve people, giving them dedicated messages based on how they use the application, their status in the company. So if they are energy managers, if they have just standard employees, or if they have employees with some competencies, with a scoring system. So we have designed a quite complex gamification engine that is able to provide dedicated feedback to users, and should be able to increase the people involvement and employees involvement in the loop. To do so, we have also created a mobile application. Here you can find just a couple of screenshots, but there is like a video. I don't know if iEnergy will share in the YouTube channel. Otherwise, I will do in our channel if you're interested. But it's like it's showing the complexity of the mobile application that is like more than 40 screenshots. if you think about screenshots, so 40 different pages where you can go through different information. So you can see the buildings, the comfort status of the buildings, the energy consumption, the consumption based on kilowatts, and the consumption based in euro at every square meters. And you have information about the costs, you have information about, you can compare shops one to each other, you have the tasks, you have alerts, and you have also, you can set the state of the HVAC system, you can interact with the application, and you have also the scoring system. Let me go ahead. And then regarding IoT contribution, so if you want to know more about what we did in the project, you have all this information. You have some information about the organization, quite simple. But if we start from the bottom, we have a case study where we more or less integrate all the different information. Okay, Then we expose a couple of models for the forecasting that we use in the first algorithm. And then we share with you, if you're interested, the 2 data sets with the real data from the 20 stores and from the 3 industrial sites, 1 year of data, hourly data. So that's also can be interesting if you want to test your own models on some open data sets. Just a last slide, I will say, regarding the impact. So the market is quite huge regarding retail companies. As I said before, this is like just a module of our platform with a monthly fee. So it's something that the user, our client, can decide to add as an add-on. So the target for us in a couple of years is to reach at least 1,500 buildings, and that will translate into a quite important turnover. Just as final remark, there are 2 benefits from the customer perspective. One is more operational, and then the second is strategic. So operational in terms that all our algorithms translate into action for employees. And this is not, it's a huge impact for a retail company where you have a headquarters with like few energy managers. You cannot really do energy saving in real time without involving employees. That's quite huge impact. And the other one is like more strategic. If you do energy monitoring and energy analysis of your shops, you change your decision making. When you design the shops, the decision that you make are based on real data and real information, are not based on something that you read on a journal or something like that. So it's something that it's like as an impact, 2 different impacts. Yeah, that's all from my side. So if you have any question.
Thank you for the presentation. I don't see any questions in the chat.
Okay. Bye. See you.
Thank you. We can move on to the next presentation with Gridable.
Hi. Hello, everybody. My name is Mirljub Krstic. I'm Business Development Manager from Modena. And just please let me show my screen. Can you see my screen?
Yes.
Okay, perfect. Well, first of all, it's a pleasure to be here and to present this solution to Energy Consortium. Electricity market is currently undergoing through fundamental transformation due to shift to carbon neutral energy sources. And what are the main challenges? Well, first of all, the role of distribution system operators is changed from energy transmitters into orchestrators of large number of prosumers. Because traditionally we have systems with small number of producers and large number of consumers. But today, with the introduction of renewable energy sources, every household or SME can be consumer and the prosumer at the same time. And secondly, renewable energy sources such as wind turbines and solar panels, they are uncontrollable. They strongly depend on weather conditions and they introduce high oscillations into energy demand. All these circumstances put DSO in the series of challenges ranging from increased operational cost to power grid failures. And the main challenge is how to orchestrate all these elements of the grid in order to ensure secure, reliable, and cost-efficient operation of the grid. Our solution to this challenge is Gridable. That is a comprehensive energy management tool that completely automates finding of optimal pattern in energy consumption and energy production. So, based on the data collected during system exploitation, Gridable automatically creates the best predictive models about production and consumption. And those models are then subjected to simulation. And through this simulation, we gain results. Then after that, we can optimize in order to get optimal operational plan. This solution is actually based on two of our modules. That is BlackFox, that is automated machine learning platform that automate completely machine learning pipeline from generation of predictive models to monitoring and finally to maintenance. And the second module that we are using is OSICE, that is optimization as a service in cloud environment. That is genetic algorithm-based optimization tool that through evolutionary process finds optimal operational plan. All these elements are actually built into our platform, Gridable, and maybe it's best that we can go live now, actually, so we can see the platform in the real world. This platform is actually operational on 4 industrial facilities in central Serbia, 3 in Čačak and 1 in Kraljevo. And as you can see on the left side, we can see a list of all producers. We can see a list of all consumers and energy storages. So if we click on some electricity producer, we can see here forecasted prediction for the next 5 days. It's obviously going to be a very bad weather in Serbia, but also we can see historical values, historical predicted values and historical real values. The same thing goes for the consumers. So if we click on some of the consumers, we can also see what is actually a predicted consumption in the next 5 days and what are the historical values. In the central part of the Gridable, we can see the current state of the system, how much electricity is produced, how much electricity is withdrawn from the grid, and so on. And we can also see a couple of financial indicators that are important to our end users. The largest part of the dashboard is occupied with the data that is necessary to produce optimal operational plan. So in the first place, that is forecasted values of production, of consumption, forecasted values for storage, forecasted electricity prices, and so on. And here you can see actually the heart of our platform. That is optimal operational plan for next 5 days. That is what is the best or optimal way to use or store electricity in the next 5 days. And as I said, this solution is employed at four industrial facilities. But we actually went one step further, and in order to produce a more intuitive and more user-friendly application, we have started the development of mobile application that will show our users all this data, but on the mobile phone. I don't know how much you can see from here, but as you can see, all the data is presented in very intuitive way, and that is something that actually our customers appreciate very much. As you can see, we are on the market with huge opportunities. European market for smart grid software is valued for over 1.2 billion euros in 2025, and the global market is valued over 5 billion euros. And we will have two pricing plans depending on the size of a DSO. So we will have license and installation private infrastructure for large DSOs, and we will have also software as a service for small DSOs. And this is our team. We have members with strong expertise in technology, with strong expertise in business. We have very strong connections to target markets. And above all, we are fully dedicated to the success of our product. Here you can see our track record. The company Vodena was established in 2015 as a spin-off of Faculty of Science, University of Kragujevac, and we are mainly active in the energy sector. And our beginnings in artificial intelligence actually were in 2017 when we received the European Commission Seal of Excellence for one of our solutions that was a dam health assessment based on evolving artificial neural networks. And in 2019, we actually developed our platform, BlackFox, that is automated machine learning platform that completely automate the whole machine learning pipeline. And after that, actually, we are using these modules mainly in the energy sector. So that would be all from my side. Thank you for your time. Thank you for your attention. And if you have any questions, please.
Thank you for the presentation. I don't think we have any questions as of now. So maybe we can proceed to the next presentation with Superpower V 2.0.
Hello, good morning, everyone. I will try to share the presentation. Let me wait a minute, please. Do you see the presentation now?
Yes.
Okay, so I will proceed. So good morning, everyone. And first of all, thanks for the Energy Consortium for being part of this second call. We develop a project as a consortium between FUVEX and Atlas. You will see afterwards which one is the role of each one. And the project is called Superpower 2.0. And it's a superpower, applying superpower resolution and automatic detection of broken insulators to power line inspections. So before starting let me pose you a question. Do you know how many kilometers of power lines are in Europe? There are more than 5 million kilometers of power line grid in Europe. So it represents a problem because it has to be inspected by law regularly. And nowadays, the type of inspection, we have two types of inspection that have been done up to today. That there are the on-foot inspection, that the cost is not so high, but the problem is they have no digital data. And also the time expended in this type of inspection is so high. And the other type of inspection is with the crew helicopters that has a higher cost, and also it has personal risk as there is a man. There are manned, so there's a person inside the helicopter, and they have a lot of emissions of harmful gases as they use fossil fuels. So here is where we find our challenge, that is develop a complete data value chain of the sector using drones, and we developed two different type of artificial intelligence tools in order to complete this data value chain and give to the end client the final result. So in the first step, as FUVEX, we are a drone operator, and in this project we developed the drone data capture first. So we have to first make a mission planning, and then before the inspection flights, in order to have everything clear and not have problems with the different aspects. And after that, we made the inspection flights. So we obtained the 2 types of images. We obtained the visual images in GP and GPG format, and the thermal images as well. So after that, we have to upload the data into the cloud, and we have to apply the first artificial intelligence tool that we are going to see in detail after, and is the enhancement of the data. In the first open call, we have done with the visual images, and in this second open call, we use this technology to apply adapted to the thermal images. So we enhance the data using this super resolution technique. And afterwards, we transfer the data to the next step, that is the Atlas one, that is the other participant of the consortium, and is the guys that use the data and make the analysis of the data in order to provide a report to the end client. So they have to receive the data, and after receiving the data and place it in the local folders, they have to make the data processing. So they process data to find the broken insulators. They have an automatic tool to detect these broken insulators. So they will give a report to the end client. So Naturgy, in this case, the UFD consortium, receives the results of the inspection, and they have the report of the defects, and afterwards they validate these results and send the results to the maintenance service provider in order to complete this inspection and correct the defects that they have been detected during the inspection analysis. So looking about the technology developed during this project, we have two different main tools developed. As I mentioned before, we have the artificial intelligence super resolution service for the capture images. So for this service, we have trained two types of generative adversarial networks, the WRGAN and the RealSGAN. And afterward, based on this generative adversarial network, we build on our own enhanced super resolution generative adversarial network. As a starting point, we have, as previously mentioned, the successful experience for the first Energy Open Call, where we apply the super resolution algorithm for the visual images. And based on that, we adapt it and we scale up to the thermal data, enhancing. We reach a 4 times increment in the number of pixels of the image. So we are gonna see here in the results what happened, and we achieve a higher value because in the visual images we have a 2 times the increment the number of pixels, and here in the thermal image we have a 4 times the increment. And here on this first image we can see in the left hand side the original thermal image that it's lower quality image than the enhanced thermal image that we have on the right hand side. And here we can see the result that I previously mentioned. We have almost a 200% in the right hand side, that is the enhanced image, and in the other side we have a 800% of zoom, and we can see the different results obtained in this type of images. And the second technology developed, the second service developed, is an artificial intelligence service for the automatic detection of broken insulator. And this is the part that it has been developed by Atlas. And this second service consists in automatically detect of broken insulator by applying this artificial intelligence tool. It's based on the YOLOnet architecture, that is you only look at once. And here we have the summary of the layers that we have been used. This is the summary of different layers. It's not only 5 layers. There are more than 100 layers used, but these layers process the information in order to, as we can see here on the example of airplanes, to construct a bounding box and identify the element that is inside the image. And basically, we have here for the creation of this dataset, we divide the images Atlas divides the images in 4 slides, and this information is labeled and then is processed. We can see here that the image has only all the time the elements in the same point of the images, as we can see here, the X and Y axis. So the elements are placed in different parts of the image depending on the image that is processed. So we have to train the system before giving the results. And finally, we can see here the results obtained. This is a more easier example where we have only 3 insulators. We have here the red ones that are the insulators that don't present any problem. And in the pink, we have here an example of a defect or a broken insulator. This missed here. You can see there are 2, and the other ones has to be 3. And here we have a more complex curve where the infrastructure has more insulators, and we detect also the insulators that are good. And here is detect that the insulator missed one of the disk. And here we can have a short video of the full prototype service demo. I don't know if it's working or not now. Basically, we have here the data capture of the, sorry about that. Yeah, we have here the data afterward is processed to obtain the enhanced photos, so the visual ones. We can see here the example of how the enhanced data is processed. So we can see the different size of the images that having the same zoom, they differ, and they give us the thermal one process. And we can see here the example as well, where the thermal enhanced module is applied, and we can see how the different images has a different resolution, the improvement of the image. And afterwards, the images are shared to Atlas, and Atlas processes the images. So we have here the images with the defect, and then afterwards we are going to see how the launch of the artificial intelligence tool is developed. And after this process, we obtain the different images, the results of the images, as you can see here as well, the example of the different insulators. And at the end of the process, Atlas makes a report, and we can see here the different images with the defects that are reported to Naturgy. And we have also a report file where we see the different numbers of the images and which one has a defect. And here is also we provide as a final element the thermal the thermal images as well to be analyzed by the Naturgy. And here we have the achieved results so far. We have the 4 times the number of pixels per thermal photo using the super resolution. We reduce the information delivery time up to 2 weeks. Instead, before with the other processes, as the helicopter or the on-foot inspection, the time could be like months. And we eliminate also the 100% of emission of using fossil fuels because we use the electrical drones, and increase the number of defect damage insulators because of the artificial intelligence tool development. we estimate that we reduce the 20% of the cost of the current means used for the full process. And at the end, we expand the customer network because we have also talked with another power line owners. We have already Naturgy, but we speak with other 3 companies that are interested in our services. And we contribute with the artificial intelligence on demand platform with 2 different data sets for high grid voltage and medium voltage grids. And we provide the software as a service, the super resolution thermal data processing, and also the artificial intelligence automatic insulator defect detection service. So that's all. Thank you very much for your attention. And again, thank you for the Energy Consortium and all the people that participate and help us during the process. I don't know if you have any question.
Thank you. Thank you for the presentation. I don't see any questions. I don't know if anybody wants to ask something. If not, we can proceed to the last presenter of the event with TrustAid.
Thank you very much.
We cannot hear you. Maybe you are on mute. Still cannot hear. No.
Can you hear me now?
Yes. Yes. Perfect.
Perfect. And can you see my screen?
Yes.
Perfect. Even better. So, hello, my name is Indre, and I'm an innovation manager at Thrust Intelligent UAV Systems. And today I'd like to present the final results of our project, TrustAid, AI-based diagnostics for aerial electricity grid inspections. So let's start with the challenge. Well, in the European Union, the total length of overhead power lines reaches a staggering 5 million kilometers, as we just heard, that need to be routinely inspected and maintained. However, current, mostly manual diagnostic practices are highly inefficient and prone to human error. We estimate that in the EU, these inspections demand more than 3 million man-hours annually. And if helicopters are involved in the aerial data collection, this results in more than 1 million tons of yearly CO2 emissions. So despite all this environmental damage, time and money put into ensuring reliability of the grid, the outages are still prevalent across the EU that lead to substantial economic losses. And our objective is to reduce these economic losses, inspection costs, and environmental impact by providing a reliable AI-based tool for timely automatic defect detection in aerial imagery of transmission power grid. So our full TrustAid solution is based on our custom high-capacity long-endurance UAVs. Our flagman drone that can be seen in this image is capable of carrying multiple high-end sensors simultaneously, including LiDAR, RGB, thermal, and other multi-sensor systems. And owing to these superior data gathering capabilities, we are able to collect extensive real-life data of power line infrastructure, which is later used for training of our deep learning models. And the abundance of high-quality training materials allows us to create an automated AI-driven analytic systems with unprecedentedly wide functionality, as we'll see later. Yeah, so during this energy project, we have focused on the development of AI-based RGB imagery analytics, which is the key component of TrustAid solution. Energy support allowed us to upgrade our RGB data analytics software from TRL 6 to TRL 7, and now we cover all types of electricity transmission network. Yes, and during our project, we have covered these functional blocks of our system development with the emphasis on data annotation and training of detection and classification models, as you can see indicated in red. We also upgraded our GIS processing algorithms, analytics workflows and pipelines, updated report formats, improved our graphical user interface, then tested the optimized whole solution. And finally, we demonstrated the full functionality and evaluated the results by comparison to manual analytics. So the summary of these analytics results was that Thrust 8 analytics solution is considered to be of sufficient functionality to address the core needs and deliver value to users as a minimum viable product. So we were happy with that. And now I'd like to quickly give some examples of our system in action. So in principle, the system analyzes aerial oblique imagery of power lines by employing multiple analytics pipelines based on fine-tuned deep learning models, and of course, GIS photogrammetric calculations to locate those defects. Here you can see in the bottom a simplified architecture. So first we detect infrastructure elements, then we classify them based on different defects, and finally analytics reports in different formats are generated. Okay, and in this slide, you can see the very basic, the easiest example of analysis, that is the insulator strings and cross-arms, because they are so large objects and there are so plenty of them, and they typically have quite many defects. So for AI, it's very easy to be trained because we have abundance of training materials. But our solution also works with, and they can, our algorithm can successfully recognize defects of much smaller elements like cable clamps or vibration dampers or counterweights, as you can see here, as well as very small elements such as conductor spacers and connections, as you can see in this example. In general, we put a very strong emphasis on training data diversity and to ensure versatility and robustness of our deep learning models. Therefore, we take care that all infrastructure variations, diverse background, lighting, and other conditions would be covered by our training data sets. Here you can see just a mesh of some data that we have used for training. And our partnership with the National Lithuania's TSO gave us access to a nationwide data of transmission network from which plenty of examples can be accumulated. So finally, when all the defects are identified, they are geolocated, characterized, and reported automatically using different formats, depending on the client needs. We are very flexible based on the report formats, because typically each client has their own set of needs and set of requirements. So we tailor our solution to a particular client. And here you can see an example of foreign, potentially dangerous objects within the protective area of the power line, with their locations indicated there in the picture on the right. And this solution we have also included in the AI on Demand platform. Okay, so this was a quick overview of the Thrust 8 analytics functionality. We will, of course, continue improving our Thrust 8 solution and use it to provide electricity grid inspections as a short-term focus. It would be inspections as a service. And in the long term, we will start selling AI-enabled drone systems and AI analytics software as a service. We really hope that with the Thrust 8 system, we will help transform the electricity grid diagnostics market by eliminating those highly inefficient manual data analytics technologies and setting new standards for inspection quality, accuracy, and speed. And in combination with our superior UAV platform that you have seen before, finally, eliminate these high-risk, climate-damaging inspection techniques, namely ground-based walking crews and helicopters in the energy sector, completely. So with this, I would like to thank our partners, the Lithuanian National TSO Litgrid, and of course, our wonderful mentor, Spiros, and his team. And it has been a really great pleasure to participate in this iNergy project. So now I'd like to thank you for your attention, and I am open for questions.
Thank you for the presentation. I don't see any questions. So lastly, I want to thank you all, the participants of the event, and of course the speakers, for contributing to the success of the iNergy project. And if there is no other questions, I think we can close the event. So wishing you all a good day. Thank you.
Goodbye. Thank you.
Thanks very much. Bye-bye.
Thank you, everyone.